In the previous video, we looked at factoring out the greatest common factor and all the terms that were in our expressions were linear terms. In other words, there was no variable raised to a power higher than 1, like an x cubed, for example. Well, what happens when you have two terms, like let's say 7x cubed plus 5x to the 5th power? And you want to know how to factor out the greatest common factor. Well, we don't have to worry about 7 and 5. There are no common factors between those numbers. But what about the variables? It looks like both terms have the variable x, but what does that mean? Does that mean that I can factor out an x? What about an x squared? What about an x cubed or x to the 4th? What exactly can I factor out of here? Well, one way to tell what you can factor out is by using the fact that you can rewrite the exponential form as repeated multiplication. So 7x cubed can really be written as 7 times x times x times x, while 5x to the 5th can be written as 5 times 5x, like that, right? X to the 5th, x times x times x times x times x. From this rewriting of the problem, it becomes very clear that they have an x in common and another x in common and another x in common. In other words, what's in common, what the common factor is x to the 3rd power, x times x times x. And we can finish the problem by saying that 7x cubed divided by x cubed is just 7, while 5x to the 5th divided by x cubed, remember when we divide we subtract the exponents, is 5x to the power of 2. 5 minus 3 is 2. Now, what you should get out of this is that the greatest common factor here, right, this x cubed, the GCF, was the x raised to the lower of the two powers. And that's really what this procedure here says. It says that if you want to find the greatest common factor of two exponential expressions that where you have the same base raised to different powers, the answer is just the base raised to the lower of the powers, right? If m is less than n, then the GCF is a to the m. So just to give you another quick example, if I had b to the 7th power plus b to the 11th power, for example, 7 is the lowest of the two powers, so the GCF that you would have to factor out is b to the 7th, b raised to the lower of the two powers. Now let's see how we can use this in a couple of examples. So example 4, we have 3x to the 9th plus x to the 5th, and we want to factor it. So we want to find the greatest common factor. 3, and there is technically a 1 here that's not written, but also not interesting, right? There's no common factors here. When we look at the x's, we have x to the 5th is the lower of the two powers. And so x to the 5th is the greatest common factor. If we divide 3x to the 9th by x to the 5th, remember we subtract the powers, we get 3x to the 4th because 9 minus 5 is 4. Plus, when we divide x to the 5th by x to the 5th, of course, anything divided by itself is 1. So plus 1. And there we go. We factored it, and there's no common factor, so we factored completely, and not difficult to check that we factored correctly. If we distribute, we get, remember, we add the exponents, we get 3x to the 9th plus 1 times x to the 5th is x to the 5th, exactly the expression we started with. Now, one thing that I would like to note is what happens if you use a different power of x? Well, what if you used x to the fourth, for example, as the greatest common factor? If you factored out an x to the fourth, then we would be dividing by x to the fourth instead of x to the fifth. And 9 minus 4 is 5. We have 3x to the fifth. And x to the fifth over x to the fourth is x to the first, or just x. So we would get 3x to the fifth plus x. And the problem would be both terms still have an x. This is not factored completely. You could factor out more. This is a great way for you to check, did you factor out everything you could? If there's a greatest common factor in here, then you did not factor completely. If you used too much, let's say you factored out an x to the sixth, then the problem would occur here when we're dividing x to the fifth by x to the sixth. We would have to get into fractions. We would have to say 1 over x, which is not what we want. That would be too much. That would be a red flag for you to say you've gone too far. Let's take a look at one more example. This one is slightly more involved. So we have 6x cubed y to the fifth minus 9x to the seventh y to the fourth plus 15x squared y to the eighth. We're going to systematically do this. This isn't particularly difficult. You just have to be systematic about it. When we figure out our GCF, we first look at the numbers. 6, 9, and 15 are all divisible by 3, so we can factor out a 3. When we look at the x's, the lowest power is 2, so that's 3x squared. And when we look at the y's, the lowest power is 4, right? 5, 4, and 8. So y to the fourth. That is our greatest common factor. And now if we divide 3x cubed y to the fifth by the GCF, oops, that should be a 6. 3x squared y to the fourth. 6 divided by 3 is 2. Oops. 2, and 3 minus 2 is 1, so that's x to the first, and 5 minus 4 is 1, that's y to the first, so we are left with 2xy, minus, when we divide 9x to the 7, y to the fourth, by the GCF, which is 3x squared y to the fourth. 9 divided by 3 is 3. When we subtract the exponents for x, 7 minus 2 is 5. And y's, 4 and 4, they cancel. There are no y's. And finally, the last term, 15x squared y to the eighth over 3x squared y to the fourth. 15 divided by 3 is 5. X is canceled, x squared and x squared. And when we subtract the powers for y, 8 minus 4 is 4. So y to the fourth. And there is our final answer. If you take time to distribute, you will see that you should get the original expression. And a very quick check, if you just look at all three terms, there is no greatest common factor other than 1, because 2, 3, and 5 don't have anything in common. Not every term has an x. Not every term has a y. So it seems like we have done everything correct.